So today we're going to talk about this paper that's been dubbed Kolmogorov-Arnold Networks, KANs, CANs, and a little bit of the chat, before we started was, about some different technologies and things, some older stuff. And I would say that this paper kind of falls into this niche of people have been building neural networks and getting gradually more and more successful. And with the transformers and large language models, there's been a lot of focus on just build things the way people have been the last few years, and take advantage.
Jerry, mute.
Oh, yeah, Jerry, you're a loud typer, you gotta mute. All right, so take advantage of the GPUs we have that are really good at matrix multiply. And if you want to do anything different, it sort of, seems to have fallen by the wayside. But, we've got Mamba that was mentioned, and we've got this, and we'll talk a little bit more about where there's so many different ideas that I think, whether they're old or they're new, that people have not tried because so much has been focused on just sort of trying to follow the well-trodden path. So let me see if I can share my screen here. Sec. All right, sorry.
Ted, I have a post. If that's not working, I can.
I also have a copy here. I managed to snag that, but it looks like you got it too.
All right. So if you guys can see my screen, I will share this. And so Warren and I are gonna talk about different aspects of this. I've got some slides, Warren's got some color, maybe some other things he can share. So that's Warren and that's me. And so if you like this talk,
True.
you can donate to our Patreon. No, actually, if you read the paper, you'll be familiar with that. This is Kolmogorov and that's Arnold on the right. And the inspiration for this paper came from some mathematical research that they did. So let's get into this paper. Here's a high-level overview of what we're going to see. So most deep neural network architectures today, they're built on top of the basic idea of a multi-layer perceptron building block. Whether you say that the transformer is exactly that or not, but it's basically built with linear layers that do matrix multiplies. And so in that sense, it really is using that same fundamental technology. If you try and draw a graph, especially like if you just look at a simple multi-layer perceptron, right? If you draw a graph of nodes and edges, the nodes are doing the interesting work. The nodes are combining the different inputs, some strongly with higher weights and some weakly with lower weights. And technically there could be negative weights too, okay? That's where the interesting stuff is happening. And there's a single nonlinearity on the output. What we're gonna see is that the building block in these CANs is gonna be very different. It's motivated by this KA representation theorem that says that you can represent any function. So that's good news, is that theoretically it's possible to represent anything. Just because it's theoretically possible does not mean that you can actually get a network to learn. That's what people learned, like say in the 80s when they were trying to build shallow neural networks to do complex functions, right? The theory said that anything could be represented by a shallow neural network with one hidden layer, but it doesn't mean that you can actually effectively teach one to do a very complex thing. So here in the CANs, what we're going to see is that you can again talk about kind of having nodes and you can have them be connected. These are sort of fully connected, just like a basic MLP. But now, instead of the interesting work happening in the nodes, the interesting work's happening in the edges. The edges will get an input from one node, and they're actually going to calculate a complex function on that input. So it could be something similar to x squared, something similar to sine of x. It could be whatever. They're going to be able to calculate complex functions on the inputs before delivering them to the next node. And then the nodes, instead of doing something intelligent, they're actually going to be really dumb. They're going to do a simple unweighted sum of their inputs. So that's just a high level sneak preview. I don't expect it to like make sense yet. Okay. The authors, I'm inferring some of this, but they fiddled around with this idea. They're like, oh, this is great. It's like all these other people tried building these networks based on this mathematical theory, and they failed. So what can I do different that they did? One of the things they did was this mathematical theory says that you need only 2n+1 nodes. It says you only need one hidden layer, a little bit like the lessons with neural networks in the 80s, right? And so they said, let's not stop there. Let's build them wider, because even though in theory we only need 2n+1, maybe it'll be easier to teach it if we go 200, right? Maybe if we go deeper, it'll be easier to teach it. And then lots of problems to solve. How exactly do you represent a complex curve, a complex function? And how do you make it so that you can teach it with backpropagation, right? It needs to be gradient descent differentiable, right? And then, well, this Ka theorem, it's actually only defined on a bounded range. So you can say on my inputs between 0 and 1, what happens when you get a 1.5? I need to handle that. So there's a bunch of things that they needed to handle, and we'll talk about some, but probably not all of them. But my feeling is that after a whole lot of pounding their head against the wall, they're like, oh, we finally got it to learn. And so they were able to show that it would learn, it would do some things. They ended up using splines to implement these complex, to approximate, complex functions. And in the paper, they have a lot of wonderful claims. They say it's more expressive per parameter, it's more accurate, and all this. But we'll see. It is more expensive than MLPs on current hardware. That's not to say that we might see a new generation of accelerators that are well designed for splines or something like that. But at least right now, it's at least like 10 times more slower to train a 1,000 parameter KAN than a 1,000 parameter neural network. And then in the paper, they really only solve toy problems. So relatively small problems that you could do just like a 3-layer KAN with, nodes you could count on your fingers, like most of them had like less than 10 nodes. So not very clear how this extends to real world problems like just cat versus dog images even. They didn't even do like MNIST or even some of your like really, really basic kind of problems. And my understanding is the reason why they didn't do MNIST is because they couldn't get it to work. It's not because like, oh, we just hit a publishing deadline. Like they actually had problems getting it to work. Since then, I think people have gotten it to work. MNIST is not that hard, so, yeah. Right? It's like whatever, 72 by 72 black and white images. So like, okay. But, I feel like for something to be considered real, you need to at least be able to get MNIST to work. So, so my high-level opinion of the paper is I'm really glad the authors did this. I think it's a solid paper. They've got an even better GitHub repo than the paper, so to speak. The paper's high quality. The GitHub repo is even better. I personally feel the hype, like on Twitter and whatever, completely does not match the paper. The paper is very interesting, and I hope people research it. But so it's this idea of we should try different things. But hey, maybe some of them should work before you like have 1 million retweets or whatever.
I do just want to mention real quick that the paper itself, like toy problems, no MNIST, didn't go super deep on it. But in terms of it being written and then getting people excited and then people building cool stuff with it, I don't know if the cool stuff has gotten to the like actionable stage, but there's definitely some cool stuff, and that's mostly what I like. I got a big list of repos here that
nice.
We can run down at some point.
Yep. Yeah. So just so you guys know, if you sense a tinge of hate in my voice when I talk about KANs, it is absolutely not directed at the paper authors, but rather, why are you guys tweeting all this stuff and writing silly articles saying KANs are going to change the world, blah, 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 blah. Like, dude, like calm down until somebody actually gets even something moderate to work on. All right, so let's go into now, how does this thing actually work, okay? So it's motivated by this Kolmogorov-Arnold representation theorem in math. So for MLPs, there's this universal approximation theorem that says, basically, if you have an infinitely wide single hidden layer neural network, it can implement this piecewise linear thing that can roughly approximate any function. And if you pick any threshold you want that it has to approximate it within epsilon squared error, it can be done. So you pick epsilon, is 0.01, done it. Okay, what if you pick 0.001? Well, you can tweak the neural network, make, whatever, and then you can do it. Okay, so as close as you want. So similarly, there's this Ka representation theorem, which is very interesting because it says that if you have a multivariate continuous function, so a function on multiple inputs, then using a fairly small number of single variable functions, just univariate functions, okay, we can compose those and add them together in a way that we can approximate as close as you want any multivariate function. So right now, if you know, it's really, really easy to learn single variable functions with a neural network. It's not easy for us to learn these complex multivariate functions. So, so this sounds very promising. So in the theorem, you basically, what you do is you say, I've got my n-dimensional problem. So let's say n is 10. I've got 10 inputs. I've got a 10-dimensional problem. So what I'm going to do is I'm going to create 2n plus 1. I'm going to create 21 functions. And these functions are only functions of one input. So things like y equals x squared, right? Things like y equals sine x. Just very, one-dimensional functions. For every single one of these 21 functions, okay, I'm going to create 10 one-dimensional functions, one for each of my input dimensions. And if I just simply take those 10, add them together, and then run my 21 functions individually, each on their on the result of the sum of those 10, then you can approximate any multivariate function you want as close as you want. So in this case, for a 10-dimensional function, you need the 21 plus the 210, so the 10 per each, right? So that's 231 univariate functions. It's kind of a lot, but it's polynomial, it's quadratic, and you can approximate. So approximately 2n squared number of functions, and you can approximate anything. Okay, so if you want to see the formula, it's down at the bottom of the page. This is the formula in the paper. Okay, so your lowercase phi, this is one where I said you're going to have 210 of these, 10 per your 21 uppercase phi's. And so you run all these functions on your input dimensions one at a time, you sum them up, and then you call this function on that scalar sum. Okay, and if you do that, then you can actually do this multivariate function. So that's the Ka representation theorem. I hadn't heard of this before. It was kind of like, wow, surprising that you could actually approximate a multivariate function using only univariate functions, and not like infinitely many of them, but just a very reasonable n squared number of them. Any questions?
Yeah, I will just for the I don't have a nearly strong enough math background just to be as excited about this as I was, but the general thing that I got from this was like, okay, there is normally a sort of like fairly complex operation that needs to happen in order for these the neural network training to complete as we expect it to. What we can do is decompose that down into these like simpler, like black box thing cause math. And so a lot of the little things make the big thing, and that's basically what I got out of it. So,
yes.
Yeah.
Exactly. So So that was an example. I said for 10, here's a drawn out example for two-dimensional. So if you have a function on 2 inputs, you're going to need 5 of these capital Phi's. You're going to need 10 of these. So for 15 total functions, you can approximate any multivariate two-dimensional function as closely as you like. You just got to get these 15 individual ones just right. Okay. The paper doesn't actually ever use specific numbers, which made it harder for me on the reading. That's why I find it much easier to just give you guys concrete examples. If it's a 2D function, you need 15 total. If it's 10D, you need 231 total. It's like a very, specific thing. All right. So
Ted, quick question. So any 2D function, this is assuming that you want to represent it with 5 in that that top layer. What is that? Is that a 5 there?
So
5?
Any continuous 2-input function, no matter how complex, no matter how wiggly, how weird, no matter what the heck it does, as long as it's continuous, with just 15 functions, you can 15 1D functions, you can represent it as accurately as you like.
So why, I get kind of the 3 multiplier, but why the 5? Where does the 5 come from?
So it's 2n plus 1, so it's 2D. So 2n plus 1, 2 times 2 plus 1 is 5 of these.
Oh, okay.
And you need 2 inputs for each of these 5, so you need 10 down here.
Okay.
And so it'll end up being 15.
Okay.
Yeah, when you mention continuous function, and considering we were discussing Mamba, there was I ran across something earlier today where the sort of hypothesis is like Mamba may not be exceedingly useful for like our traditional, traditional at this point, like transformer models that we normally work with, like large language models, but they might be really, really good at something that relies on like continuous data streams, such as like, producing real-time audio on a call or something like that. So in potentially like an interesting thing to look at is like, what are these like transformers relying on propagation like not that good at, and could we like use this sort of like univariate breakdown method to sort of like shore up some gap somewhere, is kind of like where my build stuff brain is going.
Yeah. So on the next slide, we say, okay, so if this all works, then this is like wonderful. We have a way of you just need to build 15 small little neural networks, chain them together in this particular fashion, and you're done, right? Well, there's a problem, okay? So the bad news is that the actual math theorem allows for, of your like 15 input functions to approximate any 2D function, it allows functions that are not smooth, and even functions that are like fractal dimension, okay? So those are not functions that you and I would say are a normal output of a 1D neural network, and you can't train that with gradient descent. And I don't know the math, I don't know the proof of the Ka rep theorem, but to me, it's almost like cheating. Like if you say you need a fractal function in order for this to work, it's sort of feels like cheating to me. Okay. It's like, if you guys are familiar with like the Banach-Tarski paradox, it requires you have some kind of weird like fractal subsets, and it's just really weird. It's not anything you're going to encounter in real life. But
it's a very like, well, technically you can, but
yeah. So the author basically says, hey, people tried to build things and they followed this formula where it's 2n plus 1 and there's n inputs to each of these 2n plus 1, and they kind of failed. But so they said, okay, maybe let's not just take this mathematical theorem so literally. Okay, maybe real world problems don't necessarily require some of these pathological 1D functions. Maybe for most real problems you want to solve, you can get away with just normal continuous looking 1D functions. All right. And the theorem, so for MLPs, we know this thing where the theorem says you only need one hidden layer, but deep networks just work way better. They train much faster. They're just much easier to work with. So why don't I try the same thing with KA-rep? It only requires sort of this one hidden layer in the middle. There's only one composition. There's your little phi's and your big phi's. What if I went 2, 3, 4 and just composed it? Maybe they'll actually work better. Maybe they'll train better. So the idea is like, we're not really sticking to the math of the theorem anymore, but the theorem does give us comfort that composing 1D functions is enough in order to get to complex multivariate functions. Without that theorem, you might say, well, gosh, like maybe you'll never get to anything complex if you just use 1D functions. You know what I mean? So what this says is basically like we're not following the formal theorem anymore, but we have good reason to believe that lots of high dimensional functions can be represented. And so we're going to limit our search space to get something to work to composing 1D functions. So what's the architecture? So basically, again, the original theorem said you're always going to have in this first layer, you're going to have n+1 times n functions. You're going to sum them up together n at a time, and in the second layer, you're going to have n+1. So it's a width of n+1 in the middle, and it's sort of 2 steps. So what they say is more generally, you can vary this, you can change the width, you can increase the number of steps. And so we're going to say the original KAN theorem, that picture we saw, this guy, we're going to say this is 2 layers, okay? Because there's 2 sets of functions, the bottom one and the top one, right? So we're going to say one layer has an in dimensional number of inputs and an n sub out dimensional number of outputs. Okay, so for any given layer that's n sub in and n sub out, we're just going to create n in times n out univariate functions. So we're just going to do the full, whatever you call that, cross product of every input to every output. We're going to have a function. And we're not yet saying how we're going to do that, but again, that function could look like y equals x squared, y equals log x, y equals e to the x, y equals cosine x, reasonable functions that, you and I have all heard of. And so you can imagine that, like, if you're allowed to have as complex a function as you want, you could do some pretty powerful things. So in particular, if you are doing a one-dimensional problem, let's not even get to fancy stuff. You're doing a one-dimensional problem. Well, all you need is one layer and one node, because we're saying from the input to the output, you can approximate any complex function you want, right? So even if you want like e to the sine x plus square root of x, fine. You just need one layer with one node and one in, one out, and it'll just approximate that for you. So so in that sense, nobody's saying how expensive that's going to be. Nobody's saying, but in terms of like what it can do, it can do an awful lot. All right. All right. So once again, the MLPs, if you think of them, the hidden nodes do the interesting work. Okay. They're only applying linear functions. There's no nonlinearity here. There's nothing complex. They're applying linear weights, combining the different inputs. And so I can say for this particular node, I'm going to weigh input 1 really heavily. I'm going to give it a 10. But that other input, I'm going to weigh it very little. I'm going to give it a 0.1. And we're just combining things that way. So what we're creating is a linear output, but we get to choose which inputs are more important. In the KANs, what we're going to do is instead we're going to do these complex nonlinear functions. They're still the 1D functions, okay? And the nodes are going to sum them up. And there's no activation function on the nodes. We don't need that. The activation function was there to create nonlinearities in an MLP, but we already have wiggly functions being calculated on the edges. And so things are already plenty complex. You could theoretically add an activation function. Maybe that's an interesting thing to try, but in this paper, they're not doing that. So by way of comparison, the last bullet, if you have a layer with 4 inputs and 16 outputs, if it's an MLP, it's going to have 4 times 16 weights. It's going to have 64 weights. If you have biases, okay, it'll have an additional 16 parameters for biases. And it's going to have 1 activation function that, generally speaking, in the way we build them today, it's not learned, it's predetermined based on your architecture. You say, I'm going to use regular ReLU, or I'm going to use the Gaussian one, GayLU, or I'm going to use CLU, or whatever. But you pick that in advance, generally speaking. So it's not a learned thing. And then you'll have 16 outputs. In the KAN, if you have 4 in and 16 out, you're going to have 64 of something, but instead of having 64 floating point numbers, just scalar weights, you're going to have 64 functions. And for them to be complex, we're actually going to need a lot of parameters, potentially, in order to define those complex functions if they're very wiggly. If it's just something like y equals x squared, maybe you don't need that many parameters to define it. You know, maybe a dozen is enough. To reiterate, the KAN is only operating on a bounded domain. So if I'm saying I'm going to do y equals x squared only for x values between 0 and 2, then there's this part of the curve that I have to represent, okay? We're not saying that I'm going to represent y equals x squared across all possible values of x. It's only on a bounded domain. So we have these 64 functions. We're going to group them in 4s, add them together, and if you divide 64 into groups of 4, you'll be left with 16 things. Those are your 16 outputs. And so that's the idea. And so in the same way that we think of an a stack of MLPs can get wider and narrower if we so choose, a KAN can get wider and narrower. And it's the wider you are, the more of these functions that you need to define that to connect inputs to outputs. But conceptually, you can say there's like a good, mental model for comparing. All right, are you guys still with me? Any questions? Okay. So a couple notes here, if you're following along in the paper, if you're going to read the paper afterwards, they do try to make the KANs sound as analogous to MLPs as possible. I think that it sort of helps people when you're comparing them, but going too far to try to make them analogous, I think sometimes does it a disservice. In MLPs, we have this thing called that we call an activation function, like comes from the idea of biology, and you need a certain level of activation for a neuron to fire. These 1D functions that you're learning in the KAN, they call them activation functions. I purposefully avoided using that term until just now, because they're just 1D functions. They're wiggly little functions, and they can be anything. I may have missed some of the math, but I see no connection with the concept of activation functions, okay? They call them that just because those are the only functions that we have in MLPs, and they wanted to make the connection. But if it works for you, fine, call them activation functions. For me, I actually think that confuses things. And so I just call them functions. I don't call them activation.
So Ted, you're saying that there is no trigger level or things like that for the function to fire or anything like that. It just continuously operates?
That's the general idea. So later on, we'll see an example where you're computing something like e to the sine x plus y squared, okay? And so what you'll see is that, where's my mouse? So that one of the inputs will have a wiggly curve that looks like sine, and you send x into that. And then this one, you'll send y into it, and it'll have a curve that looks like parabola that looks like y squared, okay? And then you add the two of them together, and then this function up top looks like an exponential, looks like e to the x. Okay, and that's quite intuitively, this network is going to calculate e to the sine x plus y squared. Because you did a wiggly curve that looks like sine on x, and you did a wiggly curve that looks like y squared, and you added them together, and then you ran it through e to the x. There's nothing about activation in this at all. Yeah, so there's a question about Taylor expansion. I honestly couldn't tell you whether there's any connection in the Ka representation with Taylor expansion. It is fundamentally an expansion. It is saying that any multivariate function can be expanded into approximately 2n squared univariate functions. But whether you can think of it as Taylor, or you can think of it as Fourier, or you can think it, I don't know. It is definitely an expansion, but. So yes, so for me personally, activation does not work. But again, maybe I'm missing something. So that's the activation function terminology. If you look at the paper.
Oh.
And did you want to add anything, Warren?
Yeah, I did actually. I apparently have had myself muted for quite some time.
No.
Yeah, for the I believe it's the Fourier KAN actually. The one of the discussions that I was reading through mentioned that that like looking at this repo made things make a lot more sense than the actual paper itself did. Because it's a more like kind of practical application and seems to like sort of arrange things in something that's like an interesting sort of way. I haven't gone through the repo thoroughly, but just want to drop that off.
Okay, cool. Thanks. So the other thing is that we'll see on the next slide that the authors say, so if you talk about what a layer does, where it has n in times n out 1D functions, and it sums them up in groups, and you just give that layer a name, okay? They're gonna unfortunately use capital phi, so that there's just lower and capital phis all over this paper, and they mean different things in different pages. So I did not like that. But then when you have a series of layers, you can just say you compose capital phi of layer 1 on your inputs, and then you run capital phi layer 2 on that, and you run capital phi layer 3 on that. It's like, yeah, but I could have done that with an MLP too. If I just simply said the MLP is a matrix product of all of your inputs and then a nonlinearity, then I could say the MLP is just M of layer n composed with M of layer n minus 1 composed with, it's always just some function composition. The question is whether the functions you're composing are easy or interpretable or not. And so I feel like there's a little, it's not inaccurate, but it's a little bit burying the fact that there are these nodes performing sums, because it just looks like, oh, it's just function composition. It's just Vn composed Vn minus 1, whatever. Yeah. So anyway, so I just want to warn you that it sort of belies the nature a little bit, in my opinion. And then also the final note, I already brought this up, but in the representation theorem, there are capital and lowercase phis, and then in the KAN networks, they use capital phis to describe layers, and they have lowercase phis. And so there's just these Greek letter phis everywhere, and they don't always mean the same thing, depending on whether they're talking about the original representation theorem or whether they're talking about KANs. So just a few warnings if you're gonna like go back and try and look at the paper in a little more detail. All right, so there's this nice little table. This kind of like summarizes the parallels. So in the MLP, we have the universal approximation theorem, and for KANs, we have the Ka rep theorem. This is the formula for a single layer of a neural network. You're going to multiply your input by weights, potentially add a bias, and then we're going to run a nonlinearity sigma on that. And then this formula for the KAN layer is we're going to run one set of functions, sum them up. Oh, sorry, this is the rep theorem, and so then we're going to run a second. So the shallow model for neural network looks like this, where you can't see the nodes in the middle layer, but there's a node underneath each of these ReLUs. Okay, and then for KAN, again, it's the nodes are doing sums, and you have each edge has a certain curvy function associated with it. Then this is the part I was complaining about. So the formula for a deep neural network is, weights on layer 3 composed with the activation function from layer 2, and then the weights for 2, and then the activation for layer 1 and the weights, and then this is your original input. What I'm saying is you theoretically could have combined the sigmas and the w's, and then you would have just had this nice little thing called function 3 compose function 2 compose function 1, which is exactly what they wrote here. Function 3 compose 2 compose 1. But what this is hiding is that this is not a simple function. This is a set of n simple functions then being summed. So I think that if you're going to say activations are different from weights, then in a sense you would say the same thing over here. Okay. And then here's the picture at the bottom that shows, again, what we're used to for deep neural networks is you alternate, do your weight matrix multiply, and you do a nonlinearity. And here you just have more and more, again, where you run curvy functions on your inputs and you sum them together in groups, and you can keep going as many layers as you want. So far, this is all just giving you guys a bunch of like bookkeeping, saying like, where are their functions? How many are there? This isn't really actually like telling you anything about like how this stuff works. So, but just trying to get some of the building block bookkeeping stuff out of the way. So one of the key things is you have to be able to learn a curvy function for each one of these edges, right? So that's probably, in my opinion, the biggest contribution of this paper is other people may have tried or thought about, contemplated doing something like this, but you need to figure out a way to make it learn. And these authors, to their credit, they got this thing to learn. They didn't get it to build anything big, anything real world, but they did get it so that it would learn. So what they're doing is they're using splines to approximate these 1D functions. And so I didn't know a lot about splines. I knew a little bit. If you want, you can learn more. I'm not gonna go into some of the like the YouTube videos and stuff, go into the math behind the splines, whatever. But I'm just gonna give some of the few highlights. So we're probably all familiar that if you do polynomial regression, so if you have 3 points and you fit a quadratic equation to it, if you have 11 points, you can fit a 10th degree polynomial to it. If you have 1,000 points, you can fit a 999 degree polynomial to it. And what we know is that those polynomials will become ill-behaved in between your points. There are going to be times when it's going to go to very large positive and very large negative values in between the points. And part of that is because it's constrained, it's trying to hit all of those points. And so for many real world problems, we expect that if you have nearby points, then the output of the function in between them should be very similar to the output at those 2 points. And that does not happen if you do an exact fit on the polynomial. So if you use splines, however, that does happen. The splines can be kind of curvy, but it's going to be, in the general vicinity of the output of those other 2 points. So in this particular case, like I was not familiar, but like you can take these Bezier splines and you can like decompose it into the contribution from each of the control points. And so then you can have just basically like this capital B function that represents the contribution from each of your control points. And so if you have like 10 control points for a spline, it could be fairly wiggly because you got 10 of them, right? You could theoretically go up and down 5 times. And there's this nice thing with splines that they have local behavior. So if you had 10 control points and you wiggle the 5th one, the only parts of the curve that move are the parts very close to that 5th control point. All the stuff towards the ends is going to be completely unchanged. Okay, and so you can imagine now that if you've estimated some 1D function and you were too low, you don't have to wiggle all 10 control points. You just have to wiggle the 1 or 2 control points that are nearest to where you were off. And then that's going to move the function there, and it's not going to destroy your whole function. It's not going to cause all these ripple side effects. So that's this business about splines having local behavior. So you can imagine that you can do gradient descent because you're saying, I only need to wiggle the levers that are closest to. So like if I were evaluating a function on x equals 0.3, okay, and if I had 10 control points between 0 and 1, then maybe I have to wiggle the control points at like whatever, 0.2, 0.3, 0.4, but I don't have to worry about the control points farther away than that. So I do a little bit of gradient descent, a little bit of bumping those control points in the direction that gives me a slightly better fit. And then next batch, you know, you do the same thing and just so on and so forth. So does that make sense for people how if you decomposed this spline into basis functions for each control point, that basically because of this local behavior, when you run gradient descent, you only have to adjust a couple control points. You don't have to wiggle all 10 of them in order to get the desired effect, just the nearest ones. All right, so that's what we're doing. And again, there's plenty of YouTube videos if you want to learn more about the splines. But so what you can do is there's various things you can do, but one thing you can do is you can say, hey, let me just build my small little can and see if I can approximate this, and I'm going to use 10 control points for every 1D function. I didn't get a very good loss. All right, neural architecture certs. Let's try 25 control points between for every function, because maybe it's a very wiggly function that I need to approximate and I need more control points. That was better, but it's still not a very good loss. Okay, let me try 100 control points. That's like one form of neural architecture certs that you can do with CANs. I believe, I didn't quite fully track it, but I believe there's another way in which they can sort of evaluate the function and see if the function is changing a lot. And when they notice that happening, they just dynamically say allocate more control points. This is a very wiggly function, so we better have more of them. So once again, in each layer, you're going to have the number of inputs times the number of outputs, univariate functions. In the paper, they call each of those lowercase phi. Each of those is parameterized as a spline. And then there's this weird thing that is completely not explained. In addition to the spline, they add the silu function, which is one of those common activation functions that's just like a slightly curvy, differentiable version of ReLU. Okay, so the difference between swish, silu, galu, silu, all of those, it's like, I'm not really sure what the difference is. They look so similar. They're all just curvy versions of ReLU. There's no explanation given. I haven't seen any explanation on the internet. I've seen other people mention, oh, by the way, there's this thing here, and we don't know what the explanation is. The authors never explain why that's there. I think that what this is supposed to do, this is a pure speculation, is that this helps when the network is first randomly initialized in order for it to learn, okay? It provides some nonlinearities that help the network learn. But in the long run, I think what's supposed to happen is that the silu gets, how do I say it? Learned out. So like if you had a single node and it was supposed to calculate x squared, it's not actually calculating x squared. It's calculating x squared minus silu. So that when you add the silu in, what you get is x squared, right? So that even though the silu is never physically removed from it, that basically what you're doing is you're just, instead of predicting f of x, you're predicting f of x minus CLU is what the spline is really building. And so conceptually, if you just see the curve of the output, it's as if the CLU weren't even there. Technically it's there, but like you can just sort of forget about it. That's my best guess as to what it's doing there. It's helping it learn, but it's not there for any particular mathematical reason. So I don't know if anybody wants to question or comment about that.
Yeah, I just ran I think it's not the, I don't know if we moved off the topic too far yet. I'm like bouncing between a bunch of other stuff on the side, but the I had Claude provide some like hypotheses on what to do with regard to grid extension and like architecture searches, and he's got some like interesting little thoughts. I guess I'll like drop them off in Slack, but like multi-resolution grids, or like incorporating prior knowledge about the expected smoothness and then like sort of guide the function towards the correct grid choice, et cetera, et cetera. So like some interesting sort of ideas to sort of play around with there.
Cool. Yeah, and so you can imagine the wigglier your function is, the more control points you're going to need. Okay. But so in the paper they settled on cubic splines. They're relatively easy to use. When you have G grid points, then basically every function that you're learning, you need approximately G parameters. There was also a thing about whether you have evenly spaced control points or not. And so then if they're not evenly spaced, then you need more parameters to specify where they are. I didn't really track that part. But there is this thing which I thought was quite clever. Okay. So on your inputs, the very original inputs to your KAN network, you can say, I have defined what the domain of my function is, and you can only have values between 0 and 1. Cool, because KANs only work on a bounded domain. But what about all those hidden layers in between? When you compute like 5 functions and you sum them together, maybe you're going to get a number bigger than 1. All right. So basically what they say is, okay, so if I start by defining the middle layer only takes inputs between 0 and 1, and you giving me a bunch of values in there, but you also give me a number that's like 1.2. I'm gonna take my 10 grid points that are between 0 and 1. I'm just gonna add 2 more grid points for 1.1 and for 1.2. I'll just extend it out in the direction that you need. And then later on, if you give me an input that's 1.7, it's like, now I need 5 more grid points. I'm gonna add a 1.3 or 4 or 5 or 6 and a 7. And so that I thought was like kind of a clever way of saying like we can dynamically handle you're not knowing exactly what the smallest and the largest possible input is on an intermediate layer. So if you fool me and later on I see this, I'll just do that. There's also another option where if all of your inputs are between 1 and 2, I don't really need to extend from 0 to 2. I can just shift my grid points and just represent between 1 and 2. I don't really know exactly how it works, but I'm imagining it's something like, if you imagine batch norm, it like keeps running statistics for a while, right? And so this thing can just keep statistics on a layer and say, hey, look, the smallest input I've seen is 0, and the largest input I've seen is 1.2. So I better make sure, my grid can handle up to the smallest and the biggest values. So that's a big technical thing, which I don't think is necessarily that interesting from a theoretical perspective, but I bet, oh boy, in terms of practically getting this to work, that was absolutely necessary, or else you just keep getting all of these like floating point exception, not a number errors, because you've sort of exceeded the bounds for whatever your splines defined on or something like that. So so that's very cool. And ultimately, if you're interested in doing the math, if you have L layers and they're all with N neurons, then and each function is G grid points, which now we know it's dynamic. They won't all be exactly G, but if you just stick with the simple numbers, you're going to have approximately N squared times L times G, order N squared LG parameters. Okay. All right. So this ends the bookkeeping, the technical, the building blocks, whatever part of it. the rest of the couple of slides, the rest of the paper starts to talk about like why we think they're good, and we ran and we tested, and we were able to train it on some things. So let me just pause here and just see if there's any questions about the architecture, nuts and boltsy type stuff. Yeah.
Is W also a spline in the second bullet?
This is a constant. In the paper, they actually remark that this constant could have been absorbed into the spline, but they just found that it worked better if they gave it an explicit second parameter for additional parameter for scale. So they're normalizing this spline with some very small values. When they normalize it, the spline approximates 0, y equals 0. Okay, it's not exactly that because you need, you need non-symmetry there, but it's designed to output very small values. Okay, and so I think that there's a certain like learning bias, and so it's easier for them to just throw in a constant that lets you scale it up, scale it down, than to force every grid. Like if you wanted to scale it by a factor of 10, every grid point needs to move up 10. Whereas with a single W constant, you can just grow the whole function scale-wise.
Another function decomposition.
Yeah.
Also scales the slope of the CLU.
Initially it does, yeah. Yeah, but like I said, I think the CLU is designed to sort of get absorbed into the spline and disappear.
Mm-hmm.
So
that's
I'm
why
curious,
when you see the... Please.
Oh, sorry. Go. Just looking at the Wikipedia for Kolmogorov-Arnold approximation function, there are like improvements over the year, which can get it down to 2 continuous functions that you have to approximate, and then some shifts and weights and things, which would be far fewer parameters to learn in theory. Did this paper discuss that at all?
I did not see any mention in the paper, and in fact, they were saying that really, because those functions don't need to be continuous, don't need to be normal looking, like going for the minimum is not really what you want. You want to go for sort of the easy and faster learning. Because if you think about it, our neural networks, like our CNNs, for doing images, and our transformer models, everybody's shown that once you have a fully trained network, it's very sparse. You can prune the hell out of it and like take out like 75% of the nodes, and the performance will drop by less than 10%. So it clearly is over parameterized, but it learned better than if you built a network that was only a quarter its size. So I think the same principle is likely, who knows, but likely to be true with this KAN type architecture, that there may be a minimum size, but it just might be easier to train something that's 4 times bigger and prune it than to try to nail it exactly right with the minimum necessary parts.
Okay. And are there any bounds on how fractalish the functions are given the smoothness of what you're trying to approximate? Like if I have a super smooth function like analytic or something, or Pfaffian of some finite order, like am I going to get smooth approximators, or are they still going to be crazy fractals?
I do not know the theorem. I have not read up on it. I don't know. But my guess is that, yeah, the more smooth your thing is, the less likely you're going to need something more bizarre.
Yeah.
But part of it is this idea of composing these 1Ds. That's where things are really interesting to me. That like it was not at all obvious to me that something n-squared-ish would have been enough. It's like, well, what if it's like wiggly in this particular way? Like, but the bottom line is no. The more correlated your different dimensions are, probably the easier it is to build this thing. And the more they're just sort of like really independent, like the harder it is to get all of the behaviors where, you know, when x sub 1 is low, I have this behavior on x sub 2. But when x sub 1 is high, I have a completely different behavior, right? That's the case that's going to drive you absolutely nuts, is that you have like completely region dependent behavior of your global function you're trying to approximate. That's going to suck. But again, I don't think, and then what we'll see is they tested things. So they're like, oh, here's a list of equations that appeared in Feynman's physics textbook. None of those functions are going to have that really super weirdness that I'm talking about, that for low values of input 1, it looks like a sine wave. But for high values of input 1, it looks like, you know what I'm saying? Like that is just not the way any like real world functions look. So it makes your life easier. Yeah.
Yeah. So Ted, I'm curious, have they used KAN for like classification problems? Like we only need kind of like 0 or 1 output. Because I feel like KAN looks like basically an expansion of functions, but there are some functions that cannot be expanded, like uncontinuous functions. So I'm curious, like have they done research in that?
You know, I don't remember seeing it, but there's really no reason why you can't do a final transformation. So just do a logistic function, throw a sigmoid at the end, and that'll convert from negative infinity, positive infinity to between 0 and 1, right?
Yeah.
Or other you know types necessary. So you know, if you need positive only, you can apply an e to the x to it at the end, just to do your whatever your
But like, what if like one of the inputs had kind of like determines like whether the function should go this way or that way? Like I have I have many inputs, but one of the inputs, if the value is 0, it means that the output will look like a sigmoid function. If that's 1, it means that my output would look like a sine function or cosine function. So that I feel like for neural network, like for normal neural network, then it's kind of like easy to do this job. But like I don't know if that will also work for the KN.
I can't say. Warren, feel free to either unmute or put in the chat, but I haven't seen people talking about that type of scenario. I imagine there's a way that you can parameterize it and you can represent that.
Yeah, I found a repo that has like a couple of notebooks. It's not like anything super involved, but there's like a couple of classification problems, a couple of regression problems with some notebooks to kind of play around with.
Yeah, and Julius, you mentioned indicator functions. So indicator functions not differentiable. So, but there's probably a way you parameterize and represent that concept.
Yeah, you probably just have to make them smooth, like we did with the sigmoid. Start out with tan H and then progress to Silu, Swish, Gilu. A zillion ways. But yeah, they have to be soft and differentiable.
And technically, you might have this little region in between that's a little bit fuzzy, but as long as you separate them enough, you're probably good enough for the real world.
Yeah, just set a threshold at 0.5.
Yeah.
Either fires or it doesn't, but the function has to be smooth.
All right, I'm not going to go into tons of detail, but the author talks about if you want interpretability, here's what you can do. First, you can train your KAN with L1 regularization to encourage sparsification. You can do visualization, and again, the repo has lots of cool stuff. So you can actually print out and you can look and you say, yeah, that curve looks a little bit like a sine, and that looks a little bit like a log, and that looks a little bit like an x squared. In the paper, in the details, what you see is that even after L1, well, actually, they did two kinds of regularization. There's L1 regularization and entropy regularization, but even with that regularization, it was not necessarily enough. So to get some of their really interpretable results, they did pruning where they're like, well, the weights on this are really small, so we're just going to delete that node, even after sparsification. And then the final step is this idea of symbolification, where you're like, that looks like cosine, that looks like log. So instead of the spline, I'm going to just replace it with actual cosine. I'm going to replace it with actual log. And this worked for their little toy examples, but I don't see how you rebuild GPT-2 and it's 48 layers that this is going to be a useful tool. But here's a picture of them. So you can see here, e to the sine of pi x plus y squared. You have only two inputs, x and y. It's a relatively simple function, right? It's these three moving parts, the y squared, the sine x, the e to the x. And so they built a bigger network that was bigger than what they needed. They sparsified it, and then they pruned. If you look here, you're going to see there's some faint lines here for things that were not zero, but they had low values. So then they pruned those away, and then they were just left with these three pieces. And that's when they said, you know, this curve looks like e to the x. This looks like x squared. This looks like sine x. So they sort of one at a time plug those in. And it's not just like completely by the seat of your pants saying this looks like e to the x. I believe they had like a list of common functions, and it would actually like calculate the loss and see whether it really was close. So it's not just eyeballing it, but still I personally did not find this very satisfying. So that's a symbolic regression thing. They ran it on some toy functions, so like the one we talked about, e to the sine of pi x plus y squared, and they got really accurate results. They said that it beat the MLP in terms of mean squared error on a lot of these. It's not clear to me that they picked the best MLP to compare it to, but the other thing is, in this first section, like, they know that e to the sine of pi x plus y squared is sort of the sum of two things run through a function. So I'm going to build a, where is it here? But I'm going to build a two-layer, you know, KAN that exactly fits like this. And so some of the stuff I've seen is people said, yeah, if you just build a random, like for all these functions, I'm going to build a 3-layer thing with 10 nodes in between, and just expect the sparsification and the pruning to get you your minimal. Didn't really work. Didn't always work for people. They tried some special functions here. I don't know all of these, but like the spherical harmonic functions, I think those are pretty simple and smooth. They are curvy. They'll go up and down like a sine, but they're fairly smooth and stuff. And so, you know, one takeaway is if you really are trying to do a physics or chemistry inspired thing and you think your answer is a very smooth function, maybe KANs do have the right inductive bias. But if you're doing a language model, I don't know that the English language is smooth. There's just like stupid irregularities in the English language, you know, whatever, like walked, you know, but swam. Like I don't know that swam, you know, is a nice, whatever, smooth function. It's maybe just this weird irregularity, discontinuity you need to be able to represent. So they also, like I said, tried these Feynman data sets. So there's a few more, but on the page I fit like 15. And these are functions that appear in the physics textbook. You can see these are not trivial functions. But again, I don't even know if you can compare this to MNIST in terms of complexity and weirdness, you know. And the one that has a little hook at the top of it, when is that a 1 and when is that a 7? Like, that's, I don't know. I don't know if that even just that little weird oddity, anything, you know, maybe some of these things do. Maybe some of these things have some weird differential equations, some weird properties, but, you know. They also have this example about continual learning where they said, hey, let's have this Gaussian mixture. We're going to have 5 modes, 5 peaks. And we're going to, if you look at the table below, we're going to present them one at a time from left to right. So with what we know about this grid extension business, basically what the can do is to say, oh, you gave me Gaussians between 0 and 1, and so I'm just going to approximate this. Oh, now you're giving me some new inputs between 1 and 2. I'm just going to extend my grid, and I don't have to change the values in the first part of the grid. Now you're going to give me points between 2 and 3. Well, now I can extend it again, and I don't have to. Yeah, that's great. But continual learning does not always look like I'm just going to give you numbers that are to the right of where your previous numbers were. It's I gave you cats and dogs, and now I'm going to give you bears. That's not necessarily just shift to the right. So the authors even say that they're not sure that this really applies to real world problems. So,
and what about
I give them
batch
credit.
normalization? I mean, with batch normalization, we'll shuffle all that together, and you don't have the luxury of seeing cats and dogs before bears. It's all going to come at you in random order.
Yeah. Did I go backwards? What did I do? And then again, they talked about interpretability. They had some other things they did. There was this knot theory problem that I decided not to read about, this Anderson localization. But the bottom line for me is very much so, they prove that these cans can learn, that the hidden layers, even with whatever weird stuff is happening, they'll roll with it in terms of like, you get high values, low values, negative values. So I really, again, give them a lot of credit for that. They got it to work. These things do learn, because you can easily imagine you would say, I want to build something that does 1D functions, but it can't even learn, something complicated like e to the sine x. It's just too wiggly, and it's not stationary. It just keeps going up, right? So to their credit, they got something that really can learn. They've got some heuristics for how to add more grid points if it's more wiggly, stuff like that. I'm not 100% sure about their accuracy claims, because it wasn't clear to me that they said exactly how they compared it to MLPs. And so, yeah, a 10 parameter CAN and a 10 parameter MLP, the CAN is going to win. But on the flip side, that's just this is really not fair. I mean, like, let's just talk about a really simple function, y equals x squared. Neither a gradient boosting or a neural network can do a really great job with y equals x squared, because they're sort of linear functions. So what they need to do is they just need to piecewise approximate each little subsection of. And so that's the huge advantage you have when you use splines, is that the splines will just sort of continuously curve, represent this stuff. So again, for the right problem, CANs might be really helpful, but again, not negative towards the authors, but the hype on the internet, it's like, well, but please show me that this thing works on any kind of interesting problem that we have before you really, and again, they're slow. They're very slow to train. That could be a hardware lottery thing, but right now, at least, they're slow. So, you can't really train a big CAN. And again, the CAN needs to be much, much smaller in order to be competitive with the MLP, because it's more expensive.
Does it always converge? Does it converge with probability 1 from a random initial condition?
I haven't played around on my computer, but from everything I've seen, they do seem to learn. They do seem to converge. They don't necessarily converge with the super lowest error, but yes, they seem to be pretty well behaved. Like, for example, GANs are not well behaved. Goodfellow got the thing to work, and then you tried to build a GAN, and you're like, all I got was this one image out, or it started to learn, and then it went off the deep end, and now it just shows me this thing that looks like a puddle, right? It's like, no, from what I can tell, these things are pretty well behaved. They seem to learn. They don't have vanishing gradients, exploding gradients. They don't have weird mode collapse. So they do seem to be pretty well behaved in that sense. So a lot of credit for they got it to work. And again, then there's details in there about normalize the parameters this way, and don't do this, and if this is too many, but so it worked. Again, it's using splines. They solve simple problems. And if you decide you want to play with it, there's a ton of helper functions, like the helper functions that let you visualize what each of the splines looks like. The helper functions that let you show a network with like the faded lines for the smaller weights, functions to do pruning, sparsification. So yeah, it's like really interesting. And so I just want to say, like, yeah, there was some discussion, you know, before we started about some of the old things. And Mamba was mentioned. So I think there's a lot of things that we can do. You could say I'm going to do an MLP, but I'm going to have a learned activation function instead of hard coding that every node gets gay, whatever. What if you, and the author mentions at the end, maybe there's other variants of blending of MLPs and CANs or other variants of things that are, you know, more similar. Yeah, I think so. You know, you could say maybe I won't do a full CAN version of splines with lots of grid points. But what if you just had an MLP that you let it do one cubic spline on its input? That would give it tons of degrees of freedom that a current MLP, you know, doesn't have. And then maybe you could say something like y equals x squared, which right now would take you like, you know, 50 nodes in order to like approximate reasonably well from 0 to 10. Maybe that all of a sudden you could do a cubic spline MLP and you're like, yeah, I only needed 3 nodes for that or something. I don't know.
In audio, we have the siren activation function, which is it's like sticking a sine wave in the activation function. And I don't think anybody likes it, but it just works the best. You know, they talk about it giving inductive bias for periodic signals.
Yeah.
But it looks very strange.
Right. So somebody might take that and try that with an MLP or try that with a CAN. I just feel like the space of alternate architectures really got de-emphasized because the people who just stuck with MLPs kept getting better and better results. You know, ImageNet, boom, 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 boom. And then all of a sudden, now we're doing things other than image classification. And then Transformers it, and all of a sudden, I can translate languages. I can do question answering. So it's sort of like not encouraging, you know, young PhD students to try something like a CAN, something very different, when it's like everybody who's going down the well-beaten path is just getting better and better state-of-the-art results every month, you know? So I feel like that was sort of the pressure on people, but I'm glad to see Mamba, I'm glad to see CAN, because there's, you know, no reason why it has to be an MLP. The MLP, I think, just proves that most people do not think that mammalian brains learn through backpropagation. Yet we have some super highly successful language models that do a lot of things that are pretty useful. So if we've proved that a non-mammalian architecture can actually get us some pretty advanced results, now there's zillions of other non-mammalian architectures that maybe people will apply some resources and try. You know, I think about, I don't know what's happening in medicine now, but I remember a couple of years ago reading about some guy who developed an artificial heart, and it's just a constant pressure heart. So it doesn't beat, it doesn't pulse. It's just continuous blood flow through your arteries and veins and back. And I remember the doctor said, like, yeah, you know, everything that in nature you see that flies, like birds and insects, they flap their wings, but we don't build airplanes with flapping. We build it with continuous whatever, thrust. And so he was saying, so just because nature had beating hearts doesn't mean we shouldn't have continuous. I have no idea. Maybe that was proved to be a bad idea, that your arteries, you know, under constant pressure don't do well after a long time or something. But to at least try, it seems to me like that's like a good idea. And so with neural networks, I think, yeah, let's try a bunch of different things.
Hybrid architectures seem to be the winner now, right? I mean, now it's like an attention layer, and then and maybe a gated RNN, and there's a whole lot, like Jamba is like Mamba plus attention. So hybrid seems to be the winner now.
Yeah, but to me, that's like even still too similar. Like there may be just way more different things we just haven't yet tried.
Yeah, a KAN layer, like you were saying, just try the first layer with some, especially if you know those functions are there, right? If you know that your problem should have cubic polynomial in the first layer, we you know, in the stuff that I have worked on, that's usually the case where you've got some a priori structure that you know should be there. And it's really interesting to see that they're able to get convergence, because that's usually the pitfall, is that as soon as you put in some complicated structure, the optimization goes more nonlinear, and it's not as easy to get a good result. But you know, one of the big lessons from MLPs is that, wow, they will converge from a very large, you know, trillion parameters, no problem. You know, you'll get a good local minimum even in these incredibly high dimensionalities. And you know, that was kind of a surprise. And I don't think you get that property with just any functions you pick. So you have to always check the convexity of your parameterization, and it's the you know, the sigma of matrix multiply that's the winner right now. And this is looking good, but you really have to check that really carefully.
One of the things I find interesting about this, Ted, and I don't think we're anywhere near the point where we can do this optimization, but like, you know, we've really taken a bunch of steps forward in hardware encoding some of these more complex functions as well. And then, you know, to your point about going even further away, there's also a whole field of analog processors, right, that we really haven't touched on. And if you start thinking about the lack of necessity for precision that we've proven over the last couple of years, right, as we moved from FP64s to INT8s to do the same thing, you know, it makes analog really interesting again all of a sudden, right? And the ability to approximate almost an infinite number of really complex functions using analog circuitry is fast, cheap, and you know, you can get really high density of computation. So there's just a ton of really interesting stuff. I'm sorry I missed part of the intermediary part of the talk, but I mean, as you're kind of bringing it together in this kind of idea about stretching, I also think that we're reaching the point where, I mean, and Julius, you missed the last kind of 3 sessions where we talked a lot about, holy shit, like the amount of heat being produced. You know, we're approaching the heat death of the universe to compute some of these neural networks, right? I mean, it's like it's getting to be the point where we're, you know, the entire Columbia River has been used. You know, there's not another big enough river in Oregon, so we're going to have to go to the Snake River in Idaho in order to start another AI startup. Like, and you know, or we're going to have to go to the Himalayas and catch the water earlier and use it twice on its way down Everest, right? Like, we are reaching some of the physical limitations. And so kind of getting a more creative view about how we do this, that's kind of where my brain's gone in listening to you for the last, you know, 20 minutes or so.
Yeah, that's what I like. So all indications are that if you had a data set that was 100 times the size of everything we've scraped on the internet, and you had the compute and the energy, you would actually get a better language model just using the GPT architecture, okay? So all indications are it's doable using that architecture. But so you can just find something that's more efficient. It seems like better is achievable. You just need something that's more efficient so that you don't need that much data and that much. We've gone away from inductive biases. We've gone away from the CNN has a particular inductive bias to the transformer can do anything. And I think that's wonderful, and it's probably been a necessary step to show you can do chemistry, vision, audio, all of these things. But it doesn't mean that just because you can, you should build them all that way. You know, just because you can make a car with a steam engine doesn't mean that you should stop there. You know, the internal combustion engine.
In the same way that you opened up by saying, just because you can represent any function with whatever it was, 2 to the n plus 1. You know, one of the things that neural networks went through over the last 4 years, and I've always tried to pay attention to, is the difference between the representational power of the number of neurons versus the training power of it. And, you know, the reason we have these trillions of neurons is not because we need to represent, and there's high density in those trillions of neurons. In fact, I would bet the density is less than 20%, right? But you need all of those neurons because without their structure, without that space to kind of move and learn outside, you don't learn, and it becomes untrainable. And so, yeah, I mean, again, like this is the type of thinking that your last few minutes have really kind of brought in, and as I've kind of tied it into your first comments, that there is some real interesting kind of space in here.
Yeah. So hopefully, even if CANs don't work, the interest in them will encourage other people to be bold and try alternatives, and that we will find either the theoreticians will lead us, or the experimentalists will just randomly try things and lead us to something that isn't fundamentally better. But to your point, Sally, if it learns better, then we won't need the same amount of compute in order to get the same quality language models or other models that we have.
Yeah,
They are doing that. There was an event where the CTO of Microsoft and Sam Altman were on the stage, and they were talking about how much bigger. You probably remember the big whale.
Right.
He was talking about how the power is going up exponentially, and the next version is an order of magnitude bigger, but it's also an order of magnitude more efficient. So at the same time they're scaling up, they're also coming up with efficiency gains, you know, without going into any details, but it was a solid order of magnitude in both directions in that presentation.
Cool.
Ted, in addition to kind of picking up on what Sally was talking about, in addition to just trying different architectures, I think what I'd like to see is a more exploration of what's actually going on inside of the networks that we're building. Kind of like you can train a big network and prune it down. You know, can we look at existing networks that are working well and see if there's better ways to represent what's going on inside of them?
Yeah.
Whether
I mean,
it's statistical or associative memory or splines or whatever, what's going on inside?
Yeah, that's
I mean, music to my ears. You know that I'm a huge fan of the mechanistic interpretability research, but at this point, I would say at a very fundamental level, I don't think anybody knows. It's still a mystery why MLP deep neural networks work as well as they do. Yeah. It's like, okay, here's your recipe for training this like giant, you know, GPT-4 language model. Like, it doesn't matter what random number initialization you start with. All of them will work. That's pretty freaking amazing.
Totally.
Not really, right? If you think about it, all of them work if you build a big network and then prune it. So it's, you know, indirectly saying we as humans don't know how to initialize. We just throw some numbers and, you know, hope that something sticks. And the lottery ticket hypothesis says, oh, that's exactly how it works today. And you don't need to, if you have the right set of numbers, initialization numbers, you can, you know, train a 1/10 the size of a network and still be okay.
Maybe that's it, right? Is that you're throwing more numbers at it so that 1/10 of them will actually work out. Maybe it's mode connectivity, and there's like a mathematical reason why your different local minima are all approximately identical to, you know, each other. But I mean, the reality is deep neural networks just work fabulously well, and so yeah, we just.
I like what one guy.
It's reasonable. There are other things that also work.
One guy said to me, we were talking about this. He said it's the blessing of dimensionality. In billions of dimensions, there's just too many ways down. You can just keep going down, and we just know from visualization of loss surfaces that you keep going down, and you'll just find some circuitous path around to a really good place. It may take a really long time, but there's just this incredible connectivity of basins of attraction that I don't think anybody saw coming. And so it's a nonlinear optimization that works better than it ever used to when it was a lot smaller.
Yeah. Very cool.
can think of like one application to this is I'm like my what I study is like somewhat close to physics. So usually a phenomenon is a combination of several processes, and each process we do kind of like have the set of equations. Like we do have known equations. So like what if I put like first process as a layer 1 equations, like all the possible equations, and my layer 2 as all the possible equations, and I train this KAN to see like what's the weight that will give me the best performance to fit my data. I think that would be interesting.
Yeah, it sounds like for something like that, sounds like CANs do have sort of the right inductive bias for what you're looking for.
Yeah, I think that if CAN can do that, that will be way more useful than the neural network, because people in my field, they don't just like need a general prediction. They need kind of like the concrete explanations behind everything.
Yeah, and I mean, like, you know,
But
the
they
whole
do
y equals x. Sorry, was somebody else talking?
So I was trying to find that video for everyone, and I should have been muted. I accidentally played it.
Oh, I see. Okay. So for the y equals x squared thing, you know, when I mentor beginners in machine learning, you know, I talk about if you're trying to predict housing price, and I know not all houses are like exactly rectangles, but like, you know, if you just sort of humor the analogy, if you have the length and the width of every house, and you throw it into neural network, you throw into linear regression, you throw into XGBoost, you will get something, but it won't be very good. And like probably a simple model that has only 2 inputs, but one of the inputs is the square footage of the house pre-calculated instead of the length and the width, it's going to kick your butt. And it's just because even just that simple thing of length times width, there's not really a good bias for that. But these CANs, yeah, whatever, a 2-node can like smoke you. It can calculate length times width and just, you know, be very consistent with that. So for certain problems where you don't necessarily know the right feature engineering, these CANs seem like they definitely could help with that.
Another related thing is differentiable DSP. Has anybody seen that one? That's where it's used for music synthesis, but also it's got related things in physics. You know what you want in the way of a machine. In this case, a synthesizer. The first case was an additive synthesizer, science plus noise. And so you just stick that structure in there, and but you make it differentiable. So you create any machinery you want and just make it differentiable. And then you put neural nets before it, after it, inside of it, anywhere you want. And you just have this blend of desired machinery that's differentiable and neural networks. And I think that was 2017, Jesse Engel, Google Magenta Group, and a list of authors. Very interesting stuff. And it's still very, very big in the music audio space. Every DAFX conference, you see several papers in that space. And at the ISMIR conference, there was a tutorial with a lot of code. So you can get a bunch of Python code by Ben Hayes at Queen Mary University. And it's a really great starting point if anybody wants to. So it's just another way of putting in functions that you want, and building and blending them with neural nets to taste, however you think it should go. And people are getting good results.
That seems like, Julius, I like that. That seems like a nice lesson for adjacent fields, is that if you can find a way to parameterize it and make it differentiable, then that just gives you all this wonderful flexibility versus you just have hard-coded, oh, I'm going to have this whatever, this sine wave, this triangular wave, this square wave, and I'm going to be able to do X, Y, and Z. And, you know, in theory, there's whatever composition, but like you just get all these levers when it's differentiable.
And in physics, there's a whole school of thought called PINN, which probably means something like physics I neural nets or something. And they're doing things like this where they impose the known structure and then and use the same. It's all about leveraging the gradient descent on GPUs and getting to a higher scale. You can think of it as just massive parallel computing and pseudo convex nonlinear optimization, sort of lifting the ceiling off of all these parallel fields.
I think from my knowledge, PINN physically informed neural network, they are used for solving PDE functions, partial differential equations. And yeah, and I think the problem is that first, someone pointed out they may not necessarily give out the accurate results, which like normal ways like which the traditional ways already, we do have lots of traditional ways to solve PDEs. And and second, I don't feel it's like very user-friendly to kind of like to use the PDE right now. So yeah, to use the PIN right now. And another thing is that I don't feel like lots of the problems should be solved through like the PDEs, the partial differential equations. Well, except which like give you the boundary problem, something like that.
Well, except when that's what you know you want. In other words, like if you're simulating a vibrating string, you know that the wave equation is going to be solved, and yeah, the boundary conditions, you have to deal with those. But at least in the interior of the string, you know, it's a known constraint.
Maybe put like a PANN as like one of the nodes of the KAN, so that like we let the KAN have kind of like some inputs. That we have the KAN with like several settings of the PINN and see that which one give us the best results. Because like I feel that PINN is just solving the equations. They are not kind of like adjusting the they're not kind of like choosing which equation is the best for us. But like a multiple problem is that we don't know like could this phenomenon due to equation A1 or equation 2? I think I think that would be, I think that's what KAN can do.
Yeah, so you have all these functions and you let the network tell you, you know, how to parameterize them and which ones are useful at the next layer. Kind of like, you know, MLPs where, you know, it tells you which weights you need and the ones you don't need, you can print them away later. So it's more agnostic. It's not because you don't know necessarily in advance, but when you do know in advance, it seems like worth trying. But in my experience, you can run into problems with convexity. And I think you were hinting around at doing the mixture of experts kind of approach where you would have variety of alternatives, and then you would let the downstream network decide what's most effective and successful. Is that what you were talking about? Yeah, that sounds really powerful to me.
Guys, we are over time again, like we typically are.